Hey, so welcome back, and this is another daily LeetCode problem. Today it was another graph algorithm, and it's called number of operations to make network connected. And we're given a kind of set of computers here, and we have some edges that connect them, or kind of networks that connect these computers. And we want to see, okay, what is the minimum number of operations we need to do to connect them all? And so in this case, we can see that, okay, these three are connected. We have three networks here. And so if we just break this one off, we can have all four of them connected. And so the answer is 1 in this case. And then down here, we have 6 computers, and we have 5 edges that connect them all. And we see that, okay, if we break off these 2 here, we put 1 here and 1 here, then we can connect them all. So that's 2. Then finally, there's a third case where there aren't enough cables, and we know that there aren't enough cables in this case because, well, there's we know there's 6 nodes, 6 computers, but there's only 1, 2, 3, and 4 cables, and you can never connect 6 computers with only 4 cables, and that is a kind of computer science or graph algorithm kind of rule where, say you have n number of nodes, or vertices, then you need at least like n minus 1 edges to connect them all. And so we see that in these cases where, okay, we have 6 computers and we can connect them all because we have 5 edges between them, and so that works. 1, 2, 3, 4, 5. But if we got rid of any one of these, we couldn't connect them all. And so when we have 6 nodes here, but we only have 4 edges, naturally that's not n minus 1, which is 5. So we need at least 5 edges to be able to connect them all. And so when we don't, we just return -1, okay? And so what we're gonna do to solve this is using union find. It's, when you read a problem like connecting, like it's connected components algorithm is union find. So it's literally, this algorithm is meant for solving these types of problems of, okay, what is connected? Can we connect all the nodes together? How many operations does it take to connect all of these nodes in this graph together, okay? And so to implement that, the majority of this video is just kind of creating the class, kind of implementing the union find class. And so we'll go ahead and create that. So we'll call it union, and we'll create our constructor. And I'm assuming that you're already familiar with this. You might want to read up on the data structure itself and the algorithm and the performance. But this is a great video for watching, okay, how can I write a templated solution for the algorithm and then apply it to a problem here. And so we define our constructor, and we want to pass in the number of nodes that we're dealing with. And so then we just say, okay, we want to keep track of 3 things. We want to keep track of like the number of nodes that we have. And so this is going to represent, okay, n nodes aren't connected yet, okay? And then we'll have a rank, and then we'll also have tracking the parents. Okay, equals. And so for the rank, it's just all initially going to be 0 because they're all just individual nodes that are not connected yet. And so we'll multiply it by the number of nodes that we have. And then each node is going to have a corresponding parent, and we'll just rank them from like 0, 1, 2, 3, 4, 5, because initially their parent node is themselves. And so that's just going to represent, okay, the 0 node, its parent is going to be 0. So we just do range of n to say, like, if we have 5 nodes, it would rank from 0, 1, 2, 3, 4, 5, which matches the indices. So next we have 2 other functions. The next one is the find function, usually people write out next. And this is how we're going to find the parent of the current node that we're looking at. And so we will pass in the node, which we'll just represent with x, and we'll say, okay, if the parent of x does not equal x, we'll keep looking, because we know that we'll find the root of that particular node, like the topmost parent, when its parent is itself, okay? Because the root node's parent is going to, in this algorithm, always be itself. Okay, and so what we'll want to do then is called, I forget, but this is an optimization technique. You can Google it, but if you Google union find optimizations, there's like an optimization in the find that you can do to speed up the time, and you do that by saying, okay, we're going to want to do, oh, just one sec, I got text here. Awesome. Okay, and so then we just say, okay, self dot parent of x is equal to the call to this algorithm, and we pass in self dot parent of x. Okay, so we're literally going to be setting the parent of the current node to what when we call itself, and we just pass in the parent of the current node. And by doing this, you kind of like do 2 hops at once, and that's what kind of gives you like a log n when you're doing this, because you're kind of dividing by 2 the number of hops you're going to have to do. Okay, and so once we see that, okay, the parent node of this current node is itself, then we know we've found the root. And so then we just return self.parent of x. Okay, and so now we need to define our union function, and that will be unioning x and y. Okay, and so what we pass in, or what we want to figure out, is what are the roots of these nodes. And so we say, okay, the root of x is, we just call our handy find method that we just defined here, if I can type it out. Great, and so next we just say, okay, we want to, if our x root is equal to our y root, then we just return, because we don't have to union them together, because if they both have the same root, those 2 nodes, then naturally they're already connected, so we don't have to union them together. Otherwise, we check their rankings, because this is the other optimization technique that people use, is say one node has like 5 nodes connected, and then there's like another batch over here that has like 3 nodes kind of connected in their graph. Then you'll want to add the 3 nodes as a child to like the 5 node grouping, okay? And so let's do that, and we'll say, okay, otherwise we just compare the rank. So if the rank of this root is greater than the other, then we just say, okay, let's think here. Then we say self dot the parent of our y is now going to be x, since we're linking that smaller grouping to be linked to the larger one. And so we point at the larger kind of root there. And so then we just update the rank of that larger kind of graph, and we say, okay, x root plus equals 1. Sometimes you can also just grab the rank of y root, but I typically see you just add 1 here. Great, and so then we just kind of do the exact same logic, but reverse. And so I'll just move me over here. Might as well expand that. And so then we just reverse these. So x, y, and then y. Because this is the other case where this graph is larger than this kind of set of nodes. Awesome, so let's write out the actual application to this. So what we're gonna do is we're gonna say, okay, because we're trying to find, okay, how many of these edges do we need to break off and connect here? And so we do that by first checking that edge case where, okay, what if there's not one? And so we say, okay, if there's not enough edges to connect all the vertices, and that was, okay, if the length of our connections is less than, less than n minus 1. And so we know we would want to return -1 in that case. Okay, otherwise we'll instantiate our union class, and so we say, okay, union and we pass in n, which will represent the number of nodes that we're dealing with, and we'll set that equal to u. And so next we want to iterate through all of our edges in our connections and union them together. Okay, and so let's do that. So we say for kind of I, j in our connections, we'll want to do awesome. And so we say, okay, we want to union our I and our j. Oh, and we use our u to do that. Awesome. Okay, and so now the reason why we're unioning these together is we want to see, okay, how many of these do we want to break off? And so if we're joining them, so we're saying, okay, we union this together, we union this one together, which takes 2, and say that we have 4 here, then we know, okay, to union this last one, which we can't do, that would only take kind of n minus 1 minus 2, and n is 4 in this case, which this is equal to 1. So it's saying, okay, we always know that we need n minus 1 edges to connect them all, so it's going to be 3. And so you just basically subtract the number of connected components that are already connected to get the number of nodes that aren't connected. Okay, so you're really just finding, okay, what's the number of connected components, and then you subtract the number of edges that you would need to connect them all with the number that are already connected to find what are the number of nodes that require edges to connect them all. And so what we do here is we just say, okay, self.n minus equals 1. So whenever we connect a component, we subtract 1 by the number of nodes that we have. And so that way we can say, okay, this many nodes aren't connected currently. And so we just say, okay, we want to return u.n minus 1 because you always need one less edge than the number of nodes to connect them all. Okay, so let's try running this. And success. So yeah, so just to be clear, what we're doing here is we're using the union find algorithm. We know that you always need at least the number of nodes minus 1 amount of edges to connect them all. And then you're saying, okay, if we need n minus 1 edges to connect them all, then let's just count up the number of nodes that are connected, which is 3 in this case. So then we just do, okay, 4 minus 1, which is 3, since we need 3 edges, minus the number of nodes that are connected. And since we only need 1, 2 to connect the number of edges, then you just do 3 minus 2, and that equals 1. Okay, so it's just really, I need n minus 1 number of edges. This is how many edges it took to connect the number of nodes that are connected, and then let's just subtract those to get the number of edges we need to connect the nodes that aren't currently connected. Okay, and other than that, it's just the edge case for, okay, there aren't enough edges to connect this number of nodes. So the time complexity is equal to O of the number of edges, since we're going to iterate through the number of connections. So really it's just kind of the length of that connection array. And then the space will be, oh, can't type here. Space is then just equal to O of n, because that's the size of these arrays that we're using. So it's really 2 times n, but O of n is good. Okay, so yeah, I hope that helped. It's a great question to practice. Union find is honestly pretty popular and very performant algorithm, and often does better than breadth first search, and are often simpler to understand. So yeah, I hope this explanation helped, and good luck with the rest of your algorithms. Have a great day.